All right, so topic 4.6 is on tangent line approximation. And before we get started with that, I just want to talk about what the differential of x and differential of y look like. We've been using them a lot. I just haven't given you the name. So differential of x is dx, and differential of y is dy. So that's just what that stands for. And so what we're going to do today is use the tangent line to approximate the value of a function when we don't know the equation of the function. So we can just use a tangent line that will give you something close to what the value of the function is. So if f is differentiable at c, the equation for the tangent line on or at point c, f of c, is, and it's just kind of a fancier way of doing a point slope. So we would do y minus y, but in this case, y is represented as f of c is equal to the slope, which is f prime of c, times x minus c. All right, and then a lot of times, just to kind of save some time, we would move that f of c over so it's solved for y, because we're going to actually use it. We're going to plug values in. All right, so sometimes today, instead of doing just the traditional point slope, I'm going to use this notation, but it really is found in the tangent line. It's the same thing. All right, so tangent line approximation or local linear approximation can be used to approximate values of a function that are close to the point of tangency. Okay, so we're going to do that on example 1 and 2. So we're going to use this graph and approximate what f of 1.9 is and what f of 2.4 is. So on both of these graphs, the point of tangency is at 2, 1. But the graph of f is different, and we don't know what that is. So we can't just plug in 1.9 into f because we don't know the equation. So what we'll do is find the tangent line and then use that to find an approximation. All right, so our point of tangency is the point 2, 1. So I'm going to write it the fancy way. So it's 2 f of 2 or the 0.21. All right, and then our slope of the tangent line is going to be f prime of 2. And so when we look at the tangent line, the slope, to get from this point to this point, we would go up 1, right 1. So that's a slope of 1. All right, so I'm going to go ahead and I'm going to plug all those things in to this equation. So we'll get that y equals the slope, which is 1, and in parentheses is x minus 2, and then at the end is plus 1. Now sometimes it's easier if we just plug in what we're approximating when it's in this form. For these two, I don't think it is. I think it's easier for us just to distribute the 1, which doesn't change anything, and then add like terms. This is what our tangent line is in simplest form, and because we're using it, it might be easier for it to be in simplest form. So then once we get that, what we're going to do is approximate f of 1.9. So I would say 1.9 is about right here. So that's where the tangent line is super, super close to the actual f. So what we would get when we plug it in is going to be close, a very good approximation. So it's 1.9 minus 1, or approximately 0.9. All right, and we're going to do the same thing for 2.04. We'll put that in for x in our tangent line. And we're going to get approximately 1.04. So it's on the other side of 2. It's really close. So that would be a good approximation. Now, when we look at this graph, you can tell that everywhere on the tangent line, except the point of tangency, the tangent line falls above the actual f graph. All right, so all of these points on the tangent line are above the actual function. So what that means is this 0.9 and 1.04, they are over estimation. So a little too big, but it's okay, and they're close. But they're both over estimations. All right. So let's do the same thing for example 2. So we have the same point of tangency. All right, but our slope is different on this one. F prime of 2. All right, we go down 1, right 2, so that's going to be -1/2. All right, and then I will put those in to my formula where we have the slope, and then x minus the x point, and then the y point added to the end. All right, I am going to go ahead and simplify this one as well. Just keep in mind that sometimes it's best to go ahead and leave it like this. So I'm going to multiply by that, -1/2. All right, that's my tangent line in simplest form. So I'm going to take it and I'm going to put in my 1.9, and that's going to give me an approximate value for f of 1.9. All right, and I did that earlier in the calculator. I got 1.05. All right, and then we'll do the same thing for 2.04. This is an approximation. All right. Now, when we look at this graph, the tangent line, everywhere except the point of tangency, lies below the actual graph of f everywhere. So these values that we would get from the tangent line are under estimates. Okay. Now, we actually don't have to have the graph to determine if it's an over and under estimate. We just need to know the concavity. And concavity is something we will talk about a lot. But today is the first day you're hearing that word, I think. But when a graph is concave up, it's when it looks like this. And the tangent line is going to be below the graph, and that's going to make it an underestimate. All right, so I always say concave up looks like a cup, and concave down looks like a frown. All right, and when a graph is concave down, the tangent line is going to be above the graph, so it will be an over estimation. All right, so I'm just going to go back to this previous graph and just show you the concavity. So at the beginning of this graph, this is concave down to about right there, and then the graph changes to concave up. You don't have to highlight this, right, until about right there. and then the graph changes back to concave down. So depending on where I was on this, my my tangent line could be over or under, but the point where it is, it's concave up, so it was an underestimation. Okay, so on example 3, we are going to let f be a function such that the slope is given by that derivative function. And the graph of f passes through the point 1, negative 3. That's important. And the graph is concave up between 1 and 1.5. That is also important. We're going to approximate f of 1.3 and then determine if this is an overestimation or an underestimation. All right, so we need two things. We need the point of tangency, but we have that. All right, and it doesn't necessarily tell us what to do, like to do a tangent line approximation. It just says to approximate it. So it's something you're going to have to kind of train yourself to recognize. All right, and then the slope of tangency, we're going to use the derivative graph to find that. We'll plug our point in for the x and the y. All right, so 2 times 1 is 2. Negative 3 squared is 9. And then 9 times 1/3 is 3. And that's going to be negative 1 for your slope. All right, so then we can just use that new formula we've been using where it's y equals, and we have our slope times x minus 1. And then the y part of the point of tangency is just tacked on at the end. If it's negative, you subtract it at the end. Now, if we wanted to, we could go ahead and plug the value in here. And on some of the ones on your worksheet, that is definitely easier to do at this point. This one is another one where I kind of feel like it's easier if we just go ahead and multiply it out and simplify down. All right, then it's going to be f of 1.3 is negative 1.3 minus 2. And this is an approximation. I'm really bad about forgetting to do the approximation. All right, so we don't know the equation for f, but we know at 1.3 it's somewhere close to negative 3.3. We also can figure out if this is too high or too low. So it told us in the problem that f is concave up on the interval that contains the point 1, 3. And so concave up is going to make this value be an underestimation because the tangent line is going to fall below the actual graph of f. Looks like it's spelled wrong. It's a weird word. Okay, so your assignment is going to be a worksheet that you hopefully already have, or if not, you can print it off Google Classroom, and it won't be due until right until the Monday we get back from Thanksgiving break. So I wouldn't wait too long to do it, but it's up to you. You guys have a wonderful Thanksgiving break.